So these rules for differential calculus, this table with these values on, I'm going to look at this in a second, look at the notation. But before we do that, I just wanted to point out what's going on here. Here's a function, y plotted against x, and I get some sort of curve. Okay? Differential calculus allows me to tell what about a curve at that point? Sorry? The gradient or the rate of change. Okay? If we expand this out, the trouble with it is that it's not a straight line, it's a curve. So if I take a curve, looking at this bit, say, and I try and do a gradient, draw a triangle, then it's only an approximation because it's a curve. It's not a straight line between here and here. And that's a problem. So what calculus does is it draws a triangle around a point that we're interested in and then considers what happens as that triangle gets smaller and smaller and smaller and we get closer and closer to that point. And then we talk about the limiting case when the size of the triangle becomes 0, and in other words, we're finding the gradient at a point. And the beginning of the chapter on differential calculus goes through this idea of differentiating from first principles. Luckily for us, though, the result of this exercise of seeing what happens as this triangle gets smaller and smaller and smaller is that you end up with, in the end of the day, quite straightforward results, quite straightforward rules, and all we then do is memorize these rules and use them. So we don't have to differentiate from first principles all the time. Luckily, because that's quite an involved process. We just use these rules. Okay? If you're interested in seeing where these rules come from, that we're going to talk about in a second, that's what the beginning of the chapter on calculus talks about, differentiation from first principles. But as far as an engineer is concerned, usually, where's the rule? Let me use it. Okay? That's what we're interested in doing. And here are the rules. The most important rule is this one. Okay? Because that's the general case. Some sort of function. We've got some number, a, represents the constant, and some other number, which is a power. So I've got x raised to some power, and then a number in front. For example, 4x cubed, 5x to the 5, a half x to the power minus 3. The numbers can be positive or negative or fractions. So this is the general case. And what does the rule tell us to do? It tells us to bring this power down and multiply it by the number in front to get an. So 4 times 3 is 12 here. And then it says, whatever the power is at the beginning in the function, the original function, I just take one off it. So 3 take away 1 is 2. So what's the differential of 4x cubed? 12x squared. And that's all I did in that example we were looking at earlier. So the rule is pretty straightforward. Getting to this point, getting something to look like this can be a bit awkward, and we'll look at examples like that. So, as I said before, it's not the rule that's difficult, it's the algebra leading up to the rule that can be difficult. Okay? So I'm not saying that differential calculus is always dead easy, but the rules are reasonably straightforward. If we look at the next rule, the sine function is a common function that we have to differentiate. If there's a number inside the sine function as well as the variable x, that number comes out and goes in front, and the sine changes to a cosine. And the reason for that comes from this first principles idea, but we just learn the rule. So here's an example. Here's a sine function. The 2 comes out and goes in front. So if there's a 3 there as well, I times the 3 by the 2 to get 6, which is here. And then the sine changes to a cosine. And what's inside stays the same. AX stays the same. So 2x, 2x. So differentiating 3 sine 2x, I get 6 cos 2x. Following the rule. Not too bad, right, Sam? Just got to learn the rule. The more you do, the better. Next, the cosine function. That's another common function. What happens to cosine? It changes to sine. What happens to the number inside? It comes out and goes in front and multiplies by any other number that might be there. What's the difference though? There's a minus sign in front, yeah. Okay? So if I differentiate something like 2 cos 4x, the 4 comes out, multiplies by the number in front. 4 times 2 is 8. The cosine changes to a sine, and the rest stays the same. And then I've just got to remember to put this minus sign in front. Just use the rule. The next one, this power function, where the base of the power is e, often called the exponential function, with the base e to the ax. If x is the variable, any number in front of it, a, just comes out and goes in front. So the a comes out and goes in front. And the rest stays exactly the same, look. So 3e to the 2x, I bring the 2 down, times it by the 3 to get 6, and the rest stays the same, e to the 2x. Here's a couple of special cases. If ax, this is actually an example of the first rule, but it's worth writing it down on its own. Ax, what's the power of x, by the way? 1, right. So, effectively, I bring the power down, times it by the number in front. 1 times 4 is 4. And then I take 1 off the power. What's 1 take away 1? What's anything to the power 0? No. 1. Law of indices. So we end up with just 4. So actually this is the first rule, but it's one that's worth writing down. So if you differentiate something that's just got x there, the answer is the x disappears and we're left with just the number in front. So what's the differential of x? What's the number in front of x? 1. So what's the differential of x? 1. Right. Okay. A constant, a, like a number, the differential of that is 0. And if we think about what the differential tells us, we look at this, an example of it. If I plotted a graph of y equals 12, what would it look like? Horizontal or vertical, Liam? Y equals 12. Horizontal, right. Cutting through the y-axis at 12, because it doesn't matter what x is, y is always 12. What's the gradient of that line? 0. So the rate of change of a constant is always 0. It doesn't matter what that constant is, the differential of a constant is always 0. Okay? And then finally, we've got this natural log function. We talked about logarithms, but more on that a bit later on. Okay? So it's added to these things because we use these natural logs quite a lot. It turns out the logarithm of a function is just 1 over x. If there's an a in there, that just disappears, so it's just 1 over x. The only difference is if there's a 3 in front or a number in front, that stays. So the difference of 3 log 2x is 3 over x. So those rules are quite straightforward. All you need to do now is to practice using them, and then you'll get familiar with them and you'll be able to use them easily. Okay? And that's what we need to do next.